So our mission today, as always, is to give you that shortcut to being truly well-informed on one of the most complex but also profoundly impactful scientific breakthroughs of our time, the discovery of the Higgs boson at CERN.
That's the one.
We've plunged deep into a pretty hefty stack of sources for you. Everything from the actual seminal research papers from CERN's Atlas collaboration
The primary sources, yes.
to the really personal perspectives from physicists who are right there living this quest, like Sarah Wu,
Her story is fascinating.
and also insights from places like the World Science Festival and the Royal Institution. We've tried to pull it all together.
And we're going to unpack it all. We'll look at the theory behind it, why this particle was almost, well, necessary. Then the decades-long search, which was often frustrating trying to pin it down.
Oh, yeah, the near misses.
Exactly. And the incredible technologies involved. These weren't just tools. They were engineering marvels.
Absolutely.
And crucially, the implications. Not just finding the Higgs, but finding only the Higgs. That's a huge part of the story, too.
Okay, so let's dive in.
Let's do it.
All right. To really get why the Higgs is such a big deal, we first need to talk about the blueprint, right? The standard model of particle physics.
The bedrock.
Yeah, think of it as our best, most complete understanding right now of what everything is made of, and crucially, what forces hold it all together. It's been incredibly successful as a theory.
Phenomenally successful. It's a quantum field theory built on these powerful mathematical ideas called symmetries, symmetry groups. It's basically a very precise way of describing how fundamental particles interact.
And it's so elegant, isn't it, how it classifies everything we know into just two main types, fermions and bosons.
It is neat. Let's start with the fermions. These are the matter particles, literally the stuff everything's made of.
Right.
Us, the planet, stars, everything,
All the tangible stuff.
pretty much. And they all have this quantum property called spin 12.
And it's important to remember, when we say spin, we don't mean like a little ball actually spinning, right?
No, not at all. These particles are point-like, as far as we can tell, no size. Spin is, well, it's an intrinsic angular momentum,
Yeah.
a fundamental property like charge or mass, just part of what they are.
Okay. So within these fermions, these matter particles, we've got 6 types of quarks.
The famous ones. Up, down, strange, charm, top and bottom.
And then 6 types of leptons. The electron, obviously, then the muon, the tau, and their neutrinos, 3 neutrinos.
That's the set. And it's kind of mind-blowing when you think about it. You, me, this microphone. Everything we see and touch is fundamentally made of just electrons and the tiny up and down quarks.
That's it. Everything else is more exotic, unstable stuff.
Exactly. Stable matter boils down to just those 3.
Then you have the other category, the bosons.
Right, the force-carrying particles. Unlike fermions, these guys have integer spin, usually spin 1.
Like the photon.
Perfect example. The photon carries the electromagnetic force. That's, everything from holding atoms together to chemistry to light itself, radio waves, X-rays, all photons.
Okay. And then the gluon.
The gluon carries the strong force. Incredibly powerful, holds quarks together inside protons and neutrons. Basically keeps atomic nuclei from flying apart.
Essential.
Absolutely. And finally, the W and D bosons. They handle the weak force.
Which is responsible for things like radioactive decay.
Exactly. Beta decay, for instance. And also how particles can change type, like a muon decaying into an electron. That's the weak force at work.
So we have this beautiful picture, standard model, matter particles, fermions, force carriers, bosons. Describes almost everything we measure incredibly well, but
There was this huge, glaring hole for decades. A real enigma right at the heart of it. Mass.
the problem of mass, explain that. Why was it such a problem?
Well, the standard model, in its original purest mathematical form, it worked beautifully for massless particles. But as soon as you tried to just add mass terms for particles like electrons or quarks, the whole structure broke down.
How so?
It violated fundamental symmetries, specifically something called gauge invariance, which is absolutely crucial for the theory to work consistently.
And violating that, that's bad.
Very bad. It's like, imagine building a house, but your ruler keeps changing length randomly while you measure. The whole thing falls apart mathematically. The theory becomes non-renormalizable, meaning you can't make reliable calculations or predictions. You get infinities popping up everywhere that you can't get rid of. Basically, the theory stops making sense.
So no mass allowed in the basic theory. But particles do have mass. We know they do.
Exactly. And not only did the theory not allow mass, it offered absolutely no explanation for why particles have the specific masses they do. Why is a muon, which is like a heavy electron, 200 times heavier? Why is the top quark so ridiculously heavy.
Its mass wasn't even known for a long time.
Right. It was a complete mystery until it was discovered at Fermilab. The standard model, pre-Higgs, was just silent on the origin and values of mass.
Okay, so massive problem. Literally, how did they solve it?
This is where the genius comes in. The solution was this truly revolutionary idea, proposed back in 1964 by several groups independently, most famously Robert Brout, Francois Englert, and Peter Higgs.
And also Guralnick, Hagen, and Kibble. Important to mention them too.
Absolutely. Their radical idea was, maybe the universe isn't empty space as we perceive it. Maybe it's filled, permeated with invisible, omnipresent field.
The Higgs field.
The Higgs field.
And the analogy everyone uses is...
the cosmic molasses. It's actually a pretty good one. Imagine the entire universe is filled with this thick, invisible syrup.
Okay.
Now, as particles try to move through this molasses, they interact with it. They feel a resistance, a kind of drag.
And that resistance, that's what we perceive as mass.
Exactly. Particles that interact really strongly with the Higgs field, like this super heavy top quark, feel a lot of resistance, so they're heavy.
Like trying to wade through thick treacle?
Right. Particles that interact weakly, like the electron, feel less resistance, so they're much lighter.
Like moving through water instead.
Yeah. And crucially, particles like the photon, which don't interact with the Higgs field at all.
They feel no resistance.
None. So they remain massless. They just zip through the molasses, completely unimpeded at the speed of light.
Wow. Okay, so the Higgs field is this invisible stuff everywhere. What about the Higgs boson then? That's the particle they found.
Right. The boson is the detectable manifestation of the field. It's like, think of the electromagnetic field. A photon is a ripple, a quantum, a little packet of energy in that field. The Higgs boson is the same for the Higgs field. It's a ripple, a vibration, a quantum excitation of that field. It's the physical particle, the evidence that this cosmic molasses actually exists.
So finding the boson proves the field is real.
Precisely.
And mathematically, how does this molasses idea actually give mass without breaking those crucial symmetries?
Well, that's the beauty of the Higgs mechanism. The math gets complex, but the core idea is surprisingly elegant. It involves the potential energy shape of the Higgs field.
The Mexican hat potential.
That's the one. Instead of the lowest energy state, the vacuum, being at zero field strength, like a simple bowl, it's shaped like a sombrero. The lowest energy isn't at the center peak, zero field, but down in the brim.
Okay, so the natural state isn't zero.
Exactly. The vacuum itself has a non-zero value of the Higgs field. We call this the vacuum expectation value, or VEV. It's about 246 giga-electron volts. 246 GeV.
And this non-zero background field, this VEV, what does it do?
It does something profound.
Yeah.
It spontaneously breaks the electroweak symmetry. It's like, imagine a perfectly round table with a pencil balanced on its tip right in the center. That's symmetric.
Yeah.
But it's unstable.
Right, it'll fall over.
It'll fall over in some random direction. When it falls, the symmetry is broken. There's now a preferred direction, but the underlying laws governing the pencil haven't changed. That's spontaneous symmetry breaking.
So the Higgs field falling into its non-zero VEV breaks the symmetry.
It breaks the combined electroweak symmetry, times U1 Y, down into the electromagnetic symmetry that we observe. And this breaking mechanism cleverly allows particles like the W and Z bosons and the fermions to acquire mass without violating gauge invariance.
Ah, so it fixes the renormalizability problem.
It does. It makes the whole standard model mathematically consistent and predictive, even with massive particles. It was a theoretical masterpiece. Solved the mass problem elegantly.
But it all hinged on one thing.
Finding that particle. Finding the Higgs boson, the ripple in the field. Without it, it was just a beautiful mathematical idea.
Okay, so the theory demanded it. Let's talk about the hunt, because this wasn't quick.
Oh, far from it. It was long, arduous, sometimes frustrating. And the biggest single challenge, as physicist Solon Wu often emphasized.
She was deeply involved.
Deeply, from the 80s onwards. Her point was the theory gave no clue what the Higgs mass should be. It could have been almost anything within a huge range.
So where do you even start looking?
Exactly. We knew the electron mass, the muon mass, but not why they were different. The top quark mass was unknown for ages, so experimentalists had to cast a very wide net, searching across decades of energy scales.
The first hints, or maybe false starts, came in the 80s.
Yeah, the first real flicker of excitement, though it didn't last, came from the crystal ball collaboration in 1984. They were using the Doris Collider at Dieswey in Germany.
Electrons and positrons.
Yep, they were looking at a specific rare decay of a particle called the upsilon meson. The idea was maybe upsilon decays into a Higgs plus a photon, Schultz plus Weck,
Uh-huh.
and they saw a peak, a distinct bump in their photon energy data corresponding to a Higgs mass of about 8.3 GeV gain.
0.3 GeV? That's relatively light.
It is. And the astonishing thing was the statistical significance was over 5 sigma.
Wow, 5 sigma. That's the gold standard for discovery even today.
Exactly. So huge excitement. Papers flew, theorists got busy, but unfortunately,
It wasn't real.
it wasn't confirmed. Other experiments, like CUSB at Cornell, looked and saw nothing. Even Crystal Ball, with more data, saw their own peak fade away. It turned out to be just a statistical fluctuation. Bad luck.
Ouch. That must have been disappointing.
Hugely. So that early hope vanished. Other searches in the 80s, like Syndrome, Clio, they also looked for light Higgs decaying in various ways into muons, pions, cans. Nothing.
So the conclusion was?
By the end of the 80s, the consensus was the Higgs, if it existed, had to be heavier than maybe 8 or 9 GeV. The hunt moved to higher energies.
Which brings us to CERN and the Large Electron-Positron Collider, LEP.
LEP, a beast for its time. And this is where people like Xiaolan Wu really focused their efforts. She joined the LFH collaboration at LEP specifically to hunt the Higgs.
She said she didn't realize it would take 32 years.
Ha! Yes, her quote is great. She went all in from 1980 right through the LHC discovery in 2012. LEP itself, this massive underground ring, 27 kilometers around, crossing under Switzerland and France, state of the art.
So LEP operated in phases, right? LEP-1 first.
Yes, LEP-1 ran from 1989 to 1995. It was tuned precisely to the Z boson mass, around 91 GeV. This meant it was a Z factory. It produced millions and millions of Z bosons.
Perfect for studying the Z, but how did that help find the Higgs?
Well, they looked for Z bosons decaying into a Higgs plus other particles. One key channel was Z decaying to a Higgs and a pair of leptons, electrons or muons, ZHA plus Aurea. These events are very clean, easy to spot.
Okay.
Another was Z decaying into a Higgs and a pair of invisible neutrinos, Z-Erhone. Harder to see because of the neutrinos, but it happened more often, a larger branching ratio.
And what did LEP-1 find? Or not find?
It didn't find the Higgs, but it pushed the limits up significantly. By the end of LEP-1, they had excluded a Higgs mass below about 65 GeV site. It had to be heavier than that.
Then came LEP-2, more energy.
Much more energy. From 1995 to 2000, they cranked LEP up, reaching collision energies around 200 GeVs. This was crucial.
Why?
Because now, instead of just relying on Z decays, they could actually produce a Higgs directly alongside a Z boson. The process E plus E collisions, creating HZ.
Ah, direct production.
Yes. A key search channel here involved the Z decaying leptonically, easy to see, and the Higgs decaying into quarks, which form particle sprays called jets. The 4-jet channel, where both H and Z decay hadronically, was also very sensitive.
So higher energy, new production method. Did they get closer?
They did. By 1999, the combined results from the 4 LEP experiments, ALH, Delphi HI, L3, Opal, had pushed the lower bound for the Higgs mass up again to 107.9 GeV at 95% confidence. The window was narrowing.
And then the drama in 2000.
Oh, the final year of LEP. Intense doesn't even begin to cover it.
Yeah.
The LFH experiment started seeing hints, an excess of events right near the edge of their sensitivity, around 114 GeV sort.
A potential candidate.
A potential candidate. Maybe 2-3 significance, not enough for discovery, but incredibly tantalizing. It led to this desperate push from the whole LEP Higgs working group.
They asked for more time.
They pleaded for a 4 to 6 month extension of LEP running into 2001. Just a bit more data, they argued, could push that hint over the discovery threshold. Imagine the tension.
But the request was denied.
Denied. LEP was shut down, on schedule, in November 2000. The tunnel was needed for building its successor, the LHC.
Wow. So close, potentially.
Agonizingly close. Or maybe it was just another fluctuation. We'll never know for sure what LEP would have seen with more time. But the baton was passed.
Across the Atlantic to Fermilab and the Tevatron?
Yep. For the next decade, roughly 2000 to 2010, the Tevatron near Chicago was the only game in town for the high-energy frontier, the only place actively searching for the Higgs.
And Tevatron collided protons and antiprotons.
That's right. A different approach, reaching TeV scale energies. It had 2 big, sophisticated detectors, CDF and D0, and it had major successes like discovering the top quark in '95.
But it didn't find the Higgs. Why not?
Ultimately, it came down to data volume, what we call integrated luminosity. Xiaolan Wu and others calculated afterwards that Tevatron probably needed about 2.5 times more collision data than it managed to collect to get a definitive 5 sigma discovery.
So not enough snapshots of the collisions.
Pretty much.
Yeah.
They did see hints, though. Both CDF and D0 saw a persistent excess of events in the range of 120-135 GeV, right where the Higgs eventually turned up. But the statistical significance just never got high enough, not enough certainty.
Another tantalizing hint, but no cigar.
Exactly. Tevatron had contributed hugely, narrowing the possibilities, but the definitive discovery would have to wait for the next machine.
Which brings us back to CERN and the Large Hadron Collider, the LHC,
The job.
CERN itself, the European Organization for Nuclear Research. It's more than just a lab, isn't it? It's like a mini city dedicated to physics.
It really is. You've got about 2,500 permanent staff, but then crucially, around 7,000 physicists visiting and working there from over 40 countries. It's this incredible melting pot of global scientific talent focused on fundamental questions.
And the LHC itself, the scale is just staggering.
It's hard to convey. It is without doubt the largest, most complex scientific instrument humans have ever built.
Yeah.
That same 27-kilometer tunnel is LEP, but now filled with much more powerful technology, buried 100 meters underground, crossing the border.
It's been called the world's fastest racetrack, a supermicroscope.
A cosmic DNA scanner. All true. It accelerates protons to incredible energies, smashes them together, and lets us probe conditions like those just fractions of a second after the Big Bang. Like looking back in time to understand our origins.
The engineering involved, it boggles the mind. The magnets, for instance.
Oh, the magnets are works of art. There are 12,232 main dipole magnets, each 15 meters long. Superconducting.
Meaning they have to be incredibly cold.
Colder than outer space. They operate at 1.9 Kelvin, that's 271 degrees Celsius, achieved using superfluid helium, this bizarre quantum liquid.
And the magnetic field strength.
8.3 Tesla. That's enormous. About 200,000 times stronger than Earth's magnetic field. Needed to bend those high-energy protons around the 27-kilometer ring.
And you mentioned something about it shrinking.
Yeah, this is wild. When you cool that entire 27-kilometer structure down to 1.9 K, the whole thing contracts. It shrinks in length by about 30 meters.
30 meters. How do you keep everything aligned?
With unbelievable precision engineering. Everything has to stay aligned to within microns, fractions of a human hair width, despite this massive contraction. It's an engineering nightmare, solved brilliantly.
And the energy stored in this machine.
Huge amounts. The magnetic field stores about 10.4 gigajoules. That's like the kinetic energy of a fully loaded A380 jumbo jet cruising at 700 kilometers per hour.
Wow.
And the beams themselves, when running at full power, store around 362 megajoules. That's 2 beams of protons, each with maybe 2,800 bunches, each bunch containing 100 billion protons, all traveling at nearly the speed of light. Immense stored energy.
Where do all these protons even come from?
It starts incredibly simply. A single bottle of hydrogen gas, that's the source for potentially years of operation.
Just standard hydrogen.
Yep. They strip the electrons off, get the protons, and then accelerate them through this whole chain of smaller accelerators at CERN. LINAC, then the booster, then the PS, then the SPS. Each one gives the protons a bigger kick.
Boosting them up stage by stage?
Exactly. Until they're finally injected into the main LHC ring, already going incredibly fast. By the time they collide, they're at 99.9999991% of the speed of light.
That's almost impossible to grasp. Just a tiny fraction slower than light itself.
Mere feet per second slower. It's incredible.
But it wasn't all smooth sailing. There was that incident in 2008.
Yes, the setback. September 19, 2008. Just days after the very first beams had successfully circulated the full ring, a moment of huge celebration.
What happened?
A faulty electrical connection between two of those massive superconducting magnets. A single bad solder joint, basically. It failed under high current, created an electrical arc.
Like a lightning bolt inside the machine.
Pretty much. This massive arc punctured the helium enclosure, causing a huge release of super cold helium gas and significant mechanical damage to dozens of magnets. A big section of the accelerator was badly damaged.
That sounds catastrophic.
It was a major blow, a heart-stopping moment for everyone involved. Years of work, billions invested. And this happens right at the start. People worried if it could even be fixed properly.
But they did fix it.
They did. It took 15 months of incredibly painstaking repairs and upgrades to prevent it happening again. But here's the amazing part. The resilience.
What do you mean?
While the accelerator was being fixed, the giant detector experiments, ATLAS and CMS, which we'll get to, they didn't just sit there, they kept running.
Running without beam collisions? How?
They used cosmic rays. These high-energy muons constantly rain down from space, hundreds per second, even 100 meters underground. They use these free particles to test, calibrate, align every single piece of their incredibly complex detectors.
So they turned the downtime into preparation time.
Exactly. By the time the LHC beams came back online in November 2009, ATLAS and CMS were perfectly commissioned, aligned, understood, and absolutely ready for physics data. It was an amazing recovery.
And when the collisions did start,
The LHC performed brilliantly. Run 1, from late 2009 to early 2013, started with collisions at 7 TeV total energy, then pushed to 8 TeV in 2012. It delivered about 25 inverse femtobarns of data.
inverse femtobarn, that's the measure of collected data, right? More is better.
Much better. Think of it like the total number of lottery tickets you've bought for a rare prize. 25 FU was already great. Then Run 2, from 2015 to 2018, went up to 13 TeV collision energy and reached peak performance twice the original design goal. It collected a massive 140 FU of data.
So the machine really delivered?
It over-delivered, and the sheer rate of collisions is mind-blowing. At peak performance, you get about 1 billion proton-proton collisions happening every single second inside the detectors.
1 billion per second. How do you even process that?
With incredibly sophisticated detectors and massive computing power. That rate is essential, though, because the Higgs boson production is rare. Like 1 in a billion collisions rare. You need that haystack to find the needle.
Okay, let's talk about those detectors. The eyes of the LHC, ATLS and CMS.
The two giants, general-purpose detectors designed to see everything possible that comes out of the collisions. And they are enormous. Roughly the size of a 5-story building each, weighing thousands of tons.
What's their basic job?
Fundamentally, to detect the particles emerging from the collision point, measure their properties, energy, momentum, charge, type, with incredible precision, and then computationally reconstruct the whole event, like putting together a 3D puzzle of what happened in that tiny fraction of a second.
And why 2 of them? Why not just one giant detector?
Crucial scientific redundancy and cross-checking. They were designed and built by completely separate, independent, international teams. Thousands of scientists in each collaboration.
Using different technologies.
Yes, deliberately different design philosophies and technologies. This is absolutely key. If both experiments, using different methods, see the same new phenomenon, you can be much, much more confident it's real physics, not just some weird glitch or artifact in one detector.
Like having 2 independent witnesses.
Exactly. 2 very, very sophisticated witnesses.
Let's look at ATLAS first. What's its design like?
ATLS uses a unique magnet system. It has these huge air-core toroid magnets arranged like barrels around the outside to bend muons, providing a 0.5 Tesla field. Plus, a smaller, strong solenoid magnet, 2 Tesla, in the center around the interaction point for tracking charged particles.
And inside, layers of detectors.
Layers upon layers.
Yeah.
Right near the beam pipe, you have the inner tracker, silicon pixels, silicon microstrips, and a straw tube tracker to precisely measure the paths of charged particles. Then comes calorimetry liquid argon for electromagnetic particles, electrons, photons, and other types for hadrons, protons, neutrons, pions. And the outermost layer is the huge muon spectrometer using those toroid magnets.
How big is ATLS?
It weighs about 7,000 tons. It's about 25 meters high and 44 meters long. Truly colossal.
Okay, what about CMS? Different approach.
Completely different magnet philosophy.
Yeah.
CMS is built around one single, incredibly powerful superconducting solenoid magnet. It's huge and provides a very strong, very uniform 4 Tesla magnetic field throughout its central volume.
4 Tesla. That's even stronger than the LHC main magnets.
It is one of the strongest large volume magnets ever built. This strong field bends charged particles very tightly, allowing for excellent momentum measurement within a more compact detector, hence the name, compact muon solenoid.
So CMS is smaller.
It's shorter than ATLAS, but incredibly dense and heavy. It weighs a staggering 12,500 tons. Contains enough iron, mostly in the magnet return yoke, which also houses the muon detectors, to build 2 Eiffel Towers.
12,500 tons, mostly iron.
Mostly iron in the yoke. Inside the solenoid, you have similar layers to ATLAS, but using different technologies. An all-silicon inner tracker, a crystal calorimeter made of lead tungstate, known for superb energy resolution for electrons and photons, a hadron calorimeter, and then the muon stations embedded in that massive iron yoke.
And CMS was assembled differently, too, you mentioned.
Yes, quite uniquely. Most of ATLAS was built piece by piece down in the underground cavern. CMS, however, was largely assembled on the surface in huge, multi-thousand-ton sections.
Then lowered down.
Using a pioneering system of massive gantry cranes and powerful hydraulic strand jacks. They carefully lowered these enormous slices of the detector down the shaft and into position underground, a major engineering feat in itself.
So these massive, complex machines, How did they know they were working correctly before the high-energy collisions even started? You mentioned cosmic rays.
Exactly. Those cosmic ray muons were invaluable during the construction, commissioning, and even during the LHC shutdown. Hundreds pass through the detectors every second. They act like free test beams.
What could they do with them?
Align everything perfectly, make sure all the millions of detector channels were responding correctly, calibrate the energy measurements, understand the timing, essentially debug and fine-tune the entire detector using these natural particles before the real physics began.
And once collisions started, they used standard candles.
Right. Once the LHC started delivering proton collisions, they focused first on well-understood processes predicted by the standard model. Things like producing W bosons and Z bosons, which happen relatively often and whose properties are known very precisely.
So check if you can find and measure the known stuff correctly first.
Precisely. If you can accurately measure the mass of the Z boson, its decay rates, etc., and your results match the standard model predictions perfectly, then you know your detector is working as expected. It's physics commissioned. You can trust it when it tells you something new might be happening.
It's like tuning an orchestra before the concert.
Excellent analogy. You tune with known notes before you attempt the new symphony.
Okay, orchestra tuned, detector's ready. Let's talk about the star player, the Higgs boson itself. You said it's incredibly unstable.
Vanishingly brief lifetime. It exists for less than a zeptosecond. That's less than 10 seconds. A trillionth of a second.
So it decays instantly. It never travels any real distance.
Never reaches the detector. It decays right where it's produced. So we never see the Higgs directly.
How do we find it then?
By seeing its decay products. You have to reconstruct it, infer its existence from the particles it decays into. We look for specific combinations of particles like 2 photons or 4 leptons, measure their energy and momentum, and calculate the mass of the hypothetical parent particle that decayed into them.
And look for a bump in the mass plot.
Exactly. A statistically significant excess of events clustering around a specific mass value above the expected background noise.
But you said the background is huge.
Immense. That's the needle in a haystack problem. Higgs production is rare. 1 in a billion collisions, maybe? And the particles it decays into, like photons, electrons, muons, quarks, are produced all the time by mundane, standard model processes.
So you're looking for a tiny signal buried under a mountain of noise.
Precisely. It requires sifting through petabytes of data, using incredibly sophisticated analysis techniques and statistical methods to isolate that tiny signal. It's a monumental challenge.
How is the Higgs actually produced in these proton collisions? What are the main ways?
The dominant mechanism by far at the LHC is called Gluon fusion, GGF. Accounts for almost 90%, maybe 87% of all Higgs bosons produced.
Gluons from the incoming protons fusing together.
Sort of. It's actually a quantum loop process. The gluons interact indirectly via a loop of virtual top quarks. A gluon comes from each proton, they interact through this top quark loop, and out pops a Higgs.
Interesting that the top quark is involved, even though it's much heavier than the Higgs.
Very important point. The Higgs coupling strength to particles is proportional to their mass. Because the top quark is by far the heaviest known particle, it couples most strongly to the Higgs. That's why this top quark loop dominates the production.
Okay, so gluon-gluon fusion is number 1. What else?
Next most important, about 7%, is vector boson fusion, VBF. Here, a quark inside each proton radiates a W or a Z boson. Then these two W's or Z's effectively fuse together to create the Higgs.
Does VBF have any special features?
It often leaves a characteristic signature. 2 forward jets. The quarks that emitted the WZ bosons tend to continue down the beam pipe and create jets of particles in the forward and backward directions. Seeing those jets can help tag VBF events.
Okay, what other ways?
There's associated production, where the Higgs is produced alongside a W or a Z boson. We call this VH production, where V stands for vector boson. That's about 5%.
So you'd see a Higgs decay plus a W or Z decay in the same event?
Exactly. And finally, there's the rarest, but very important, mode, associated production with a pair of top quarks, TTH production.
Higgs produced alongside 2 top quarks. That must be rare, since tops are so heavy.
Very rare. Only about 1% of Higgs production. But it's absolutely crucial because it directly probes the Higgs coupling to the top quark, its strongest coupling. Measuring this precisely is a key test of the standard model and a window to potential new physics.
And they've actually seen TTH.
Yes. A major achievement of LHC Run 2 was observing TTH production definitively. Both ATLS and CMS have measured it now with high significance, confirming the top Higgs coupling.
Okay, so that's how it's made. How does it die? What are the key decay channels they looked for? especially for the discovery.
For the discovery, the high-mass resolution channels were absolutely king. These are decays that allow you to reconstruct the Higgs mass very precisely, giving you a sharp peak rather than a broad bump.
Makes the signal easier to spot.
Much easier. The absolute golden channel is HEZZZ, 4Yo.
Higgs to 2 Z bosons, then to 4 leptons. What does the star on the Z mean?
It means one of the Z bosons can be virtual or off-shell. Since the Higgs mass 135 GeV is less than 2 Z masses, about 91 G each, one Z has to be produced with less than its normal mass, but it still decays the same way.
And 4 means 4 leptons.
4 leptons,
Yeah.
either 4 electrons, 4e, 4 muons, or 2 electrons and 2 muons, 2e2.
Why is this channel golden?
Because leptons are relatively easy to detect and measure precisely. And seeing 4 high-energy leptons originating from the same point is an incredibly clean signature. The background noise from other processes faking this signature is very, very low.
Even though the decay rate is small, only about 2.6%.
Tiny branching ratio, yes. But the cleanliness makes up for it. You don't need many events to see a clear signal. The analysis requires finding 4 isolated leptons, passing certain energy thresholds, and checking their combined invariant mass.
Okay, the 4-lepton golden channel. What else was crucial for discovery?
The other really key high-resolution channel was H-Giger, Higgs decaying into 2 high-energy photons.
2 photons, that sounds clean too.
Very clean signature. 2 distinct spikes of energy in the electromagnetic calorimeter with no associated charge particle tracks. But this channel's even rarer branching ratio is only about 0.2%.
Wow, 1 in 500 Higgs bosons decay this way.
Roughly. And interestingly, this decay also happens via quantum loops, primarily involving WO bosons and top quarks. This makes it sensitive to potential new heavy particles that could also contribute to the loop.
So it's a discovery channel and a probe for new physics.
Exactly. Finding it required sharp triggers, high energy thresholds for the photons, and careful analysis of the shower shapes in the calorimeter to distinguish real photons from background, like energetic neutral pions decaying.
So H-rare and HAGO were the discovery workhorses. What about other decays?
There are decays with much larger branching ratios, but they are low mass resolution or have huge backgrounds, making them harder for discovery but vital for later studies.
Like H-rare W plus W, that's the biggest decay rate, right? Around 21%.
It is, but when W bosons decay, especially into leptons, they produce neutrinos, and neutrinos fly right out of the detector without being seen, carrying away energy and momentum.
Which messes up the mass reconstruction.
Badly. You can't precisely calculate the mass of the parent particle if you don't know the energy of all the children, so HAWs are messy.
What about decaying to tau-s? H-air plus 1? About 6%.
A similar problem. Tau leptons also decay very quickly, often producing neutrinos. So again, difficult mass reconstruction.
And the decay with the absolute biggest rate. HOBA, Higgs to 2 bottom quarks. Nearly 60%.
By far the most common decay, about 58%.
Yeah.
But the background is astronomical.
Why?
Because standard QCD processes, just quarks and gluons interacting, strongly produce pairs of bottom quarks like crazy at the LHC. The background rate is something like 10 million times higher than the Higgs signal.
10 million times? How can you possibly see the signal?
It's almost impossible in direct production. The searches for HO focus almost entirely on associated production, like VH or TTH.
Where the Higgs is produced alongside a W, Z, or top quarks.
Yes. If the W or Z decays leptonically, that gives you a clean tag isolated leptons missing energy that helps suppress the overwhelming QCD background. Then you look for 2 B quark jets in the event. It's the only way to dig out the AJ signal.
Okay, that makes sense. Incredible challenges. Which brings us to the announcement. July 4th, 2012.
The day the particle physics world had been waiting for decades. The culmination.
Things had been heating up before that, though. December 2011.
Yes, that was the first public hint. Both ATLAs and CMS presented their preliminary results based on the 2011 data run at 7TV, and both showed tantalizing hints, small excesses of events, maybe 2-3 sigma each, right around 125 GeV, in both the 4-lepton and diphoton channels.
Not enough for discovery, but pointing in the same direction.
Exactly. 2 independent experiments seeing hints in the same mass region in 2 different clean channels. The buzz was incredible, but they needed more data.
Which came in 2012 with the energy increase to 8 TeV.
Right. The LHC ran flat out in the first half of 2012 at 8 TeV, collecting data faster than ever. And the analysis teams worked furiously. Crucially, they followed strict blind analysis protocols.
Meaning they didn't look at the actual signal region in the data.
Correct. They finalized all their analysis procedures, background estimations, statistical methods using simulated data, Monte Carlo, and control regions in the real data before opening the box and looking at the critical Higgs mass region.
Why is this so important?
To avoid unconscious bias. If you see a small fluctuation, you might subconsciously tweak your analysis to enhance it. Blinding prevents that. You define the rules before you see the result. It ensures objectivity, especially when the stakes are this high.
So the moment of truth was unblinding the data.
Sometime in June 2012, both teams independently unblinded their ATV data and combined it with the 2011 results. And the signals just jumped out. Clear, unambiguous peaks right around 125 GeV.
And they reached the magic number, 5 sigma.
They exceeded it. In particle physics, 3 sigma is called evidence, but it might still be a fluke. 5 sigma is the gold standard for discovery.
How unlikely is a 5 sigma fluctuation?
It corresponds to a probability of about 1.7 in a billion that the observed signal is just a random background fluctuation. Incredibly unlikely. It means you've almost certainly found something real.
Like rolling dice and getting the same unlikely number so many times, the dice are loaded.
That's a good way to think about it. The bump hunting revealed a peak that was just too statistically significant to ignore. And it was achieved by combining the power of both the AGR and HEA channels, and then, critically, combining the results from both ADR and CMS. The consistency was undeniable.
Which led to the historic announcement seminar at CERN, July 4th, 2012.
An electrifying event, broadcast worldwide, packed auditorium. And sitting right there in the front row were Peter Higgs and Francois Englert, two of the original theorists, seeing their 1964 prediction confirmed nearly 50 years later. Must have been an incredible moment for them.
And both experiments presented their results.
Yes. First CMS, then ATS. Both independently announced the observation of a new particle, a narrow resonance, with a mass around 125 GeV, consistent in every way measured so far with the standard model Higgs boson. Standing ovations, tears. A truly historic moment for science. And it's worth remembering that ATLs included a dedication in their discovery paper.
Right, to colleagues who didn't live to see it.
To the memory of our ATL's colleagues, who did not live to see the full impact and significance of their contributions. It really highlights the human side, the decades of collective effort, the generations of scientists involved in these massive projects.
A powerful reminder. Okay, so they found a new particle at 125 GeV. The next question, was it the standard model Higgs?
Exactly. Finding a bump is step 1. Characterizing it is step 2, 3, 4, and ongoing. First, confirm the mass, settled around 125 GeV okay. But what about its other properties?
Like spin and parity. The standard model predicts it should be what?
A scalar, spin narrow with positive parity, denoted 0 plus UC. This is really unique. All the matter particles, fermions, are spin 12. The known force carriers, photon, WZ, gluon, are spin 1. Finding a fundamental scalar particle would be a first.
So did they test that?
Oh, yes.
Yeah.
Extensively. They looked at the angular distributions of the decay products in channels like AZZ4 and EGV. These distributions depend critically on the spin and parity of the parent particle.
And the results?
Overwhelmingly favored the spin 0, positive parity, 0 plus hypothesis. They tested it against other possibilities, like spin 0 negative parity, pseudoscalar, 0, or spin 1, spin 2. All those alternatives were strongly excluded. CMS ruled out 0 wanted at 99.8% confidence, ATLAs at 98%.
So it looked like a scalar, a huge checkmark for the standard model Higgs.
A massive confirmation. It really started to look like they had found the Higgs boson predicted by the theory.
What about its interactions? Does it couple to other particles the way the standard model says it should?
That's the core of the ongoing research program at the LHC. Measuring the Higgs couplings. The standard model makes very precise predictions. The Higgs should couple to particles proportionally to their mass.
Heavier particles interact more strongly with the Higgs field boson.
Exactly. So the coupling to the top quark should be strongest, then to the W and Z bosons, then bottom quark, tau lepton, and so on, down to the lighter particles. Measuring these coupling strengths is a key test.
How do they measure them?
By precisely measuring the rates of Higgs production via different mechanisms, GGF, VBF, VH, TTH, and the rates of its decay into different channels. GO, ZZ, WW, BB. Each rate depends on specific couplings.
So you measure how often it decays to W's versus Z's versus taus.
Exactly. And compare those ratios and the overall rates to the standard model predictions. For example, measuring HAWW and HEZZ tested the couplings to gauge bosons. Measuring HU-Bo and He+, directly probes the Yukawa couplings to fermions, how it gives mass to matter particles.
What about Hego? That happens via loops.
Right. The AG rate depends on the couplings to the heavy particles running in the loop, mainly the W boson and the top quark. So it's an indirect but sensitive probe, and any new undiscovered heavy particles could also contribute to that loop, potentially altering the rate.
So deviations from the predicted rates could signal new physics.
Absolutely. That's what everyone is looking for. So far, the measurements are remarkably consistent with the standard model predictions within the current uncertainties.
They've even seen the decay to muons now, Hia.
Yes, another recent triumph. Muons are much lighter than cassis or bottoms, so the 8-K is very rare, about 0.02%. Observing it confirms the Higgs couples to second-generation fermions, as expected.
What about decays to electrons? Age or charm quarks?
Aki is predicted to be incredibly rare, maybe 100 times rarer than Helium, so not seen yet. He is really tough because distinguishing charm jets from the overwhelming background of other jets is extremely difficult, still being worked on.
And confirming the TDH production rate was important too?
Crucial. It directly measures the Higgs top coupling, the largest coupling. Again, so far, consistent with the standard model prediction. All these precise measurements are tightening the screws on the standard model, looking for any crack where new physics might be hiding.
Okay, so the standard model looks great. The Higgs fits perfectly, almost too perfectly.
That's the irony, isn't it? The standard model is incredibly successful, predicts things like the electron's magnetic moment to parts per billion accuracy. Just astonishing. But it's clearly incomplete. It describes the ordinary matter and forces, which make up only about 5% of the total energy density of the universe.
95%. What about the other 95%?
That's the great mystery. About 27% is dark matter. This invisible stuff that doesn't interact with light, we only detect its gravity holding galaxies and clusters together. The standard model has no particle candidate for dark matter. None.
And the rest? The biggest chunk?
About 68% is dark energy. This even more mysterious something causing the expansion of the universe to accelerate. We have almost no idea what it is. Could it be related to vacuum energy? Maybe another scalar field? The standard model is silent.
So dark matter, dark energy. What else does the standard model not explain?
Well, the matter-antimatter asymmetry. Why is the universe made almost entirely of matter when the Big Bang should have created equal amounts of matter and antimatter according to the standard model? Where did the antimatter go? The SM has a mechanism for asymmetry, but it's way too weak to explain what we see.
And the weakness of gravity.
The hierarchy problem. Why is gravity so incredibly feeble compared to the other forces, electromagnetism? Weak, strong. It's weaker by like 30 or 40 orders of magnitude. It seems unnaturally weak. The standard model offers no explanation.
Okay, huge unanswered questions. Do theories beyond the standard model try to address these? And how does the Higgs fit in?
Absolutely. Lots of theories. One of the most popular for decades has been supersymmetry, or USY.
USY, what's the basic idea?
It proposes a new fundamental symmetry between the two types of particles: fermions, matter, and bosons, forces. For every known fermion, ADOSY predicts a boson partner, a sparticle, and for every known boson, a fermion partner.
So doubling the particle zoo.
Pretty much. Selectrons partner electrons, quarks partner quarks, photinos partner photons, Higgsinos partner Higgs bosons, and so on.
Why is SOPHIS-Y attractive? What problems does it solve?
Several. For one, the lightest supersymmetric particle, LSP, if stable and neutral, is often a perfect candidate for dark matter. Solves the 27% problem naturally.
Okay, that's big.
Also, CSY can help stabilize the Higgs mass against potentially huge quantum corrections related to the hierarchy problem. And it beautifully allows the strengths of the three standard model forces to unify at very high energies. Many appealing features.
What about other ideas like extra dimensions?
Also trying to tackle the hierarchy problem, mainly. The idea is maybe there are more spatial dimensions than the three we see, but they're tiny, curled up. Gravity might be strong fundamentally, but it leaks into these extra dimensions, making it appear weak to us.
And this could lead to things like micro black holes at the LHC.
In some models, yes. If the extra dimensions are large enough, the energy needed to create tiny black holes could be within reach of the LHC. But as we said, they'd evaporate instantly via Hawking radiation, a very exotic signature.
But the LHC hasn't seen any sparticles, no micro black holes, no signs of extra dimensions.
Nothing. And that's the shock. The discovery of only the standard model Higgs, with no other new particles popping up alongside it at the energies probed so far? This was profoundly unexpected by most theorists.
Why was it so shocking?
Because theories like USY, designed to solve problems like the hierarchy problem, generally predicted that the new particles, shouldn't be too much heavier than the Higgs itself. They were expected to be within reach of the LHC. Their abscess is a huge puzzle.
So finding just the Higgs is harder to explain.
In some ways, yes. It challenges the theoretical frameworks developed over decades. Why is the Higgs mass what it is? Why is the electroweak scale so much lower than the scale where gravity becomes strong, the Planck scale? Without new physics nearby, the standard model seems fine-tuned, unnaturally balanced. It's a deep conceptual challenge.
Like the Michelson-Morley experiment disproving the ether, it forced a rethink.
Exactly. It suggests nature might be simpler or perhaps more subtle than many of our theories anticipated. It forces physicists back to more fundamental questions. Why this particular Higgs? Why this mass?
So where do we go from here? What's next for particle physics?
The immediate future is the high luminosity LHC, the HL-LHC, a major upgrade to the existing machine.
Starting when?
Around 2029. The goal is to crank up the collision rate, the luminosity, dramatically, aiming to collect about 3,000 inverse femtobarns of data by the mid-2030s.
That's 10 times the original LHC design goal, and way more than collected so far.
It's a huge data set. The mission of HL-LHC is precision, make incredibly precise measurements of all the Higgs boson's properties, its couplings, its rare decays, search for tiny deviations from the standard model.
And maybe even measure how the Higgs interacts with itself. It's self-coupling.
That's a key goal. Measuring the Higgs self-coupling is extremely difficult, but crucial for understanding the shape of that Mexican hat potential. HL-LHC should provide the first real sensitivity to it. It will also extend the search for new, heavy particles to higher masses.
Pushing the boundaries with precision and statistics, what about beyond HL-LHC?
Looking further ahead, the big dream is a next-generation collider. Several proposals are on the table, but a leading contender is the Future Circular Collider, FCC.
Bigger ring.
Much bigger. A 100-kilometer circumference tunnel, potentially. Capable of reaching maybe 100 2B collision energy for proton collisions.
100 TV. Compared to LHC's 1314 TV, that's a huge leap.
A massive leap in energy reach. A true discovery machine, potentially able to directly produce particles far heavier than the LHC can reach.
But the FCC could also run electrons and positrons.
Yes, that's a key part of the plan. It could start as an electron-positron collider, a Higgs factory. Colliding electrons and positrons provides a much cleaner environment than proton collisions.
Why is that useful?
You could produce millions, maybe billions, of Higgs bosons in pristine conditions. This allows for unbelievably precise measurements of its properties, far beyond even the HL-LHC. Testing its couplings to exquisite precision, searching for tiny forbidden decays, really pinning down its nature. Is it truly point-like? Does it couple exactly as predicted?
Probing the Higgs with unprecedented accuracy.
Exactly. It's the ultimate precision tool for understanding the scalar sector of nature.
And these incredibly small-scale physics questions, they connect back to the cosmos.
Profoundly. The Higgs field isn't just important now. It likely played a critical role in the very early universe.
Like cosmic inflation.
Possibly. Some theories suggest a field very much like the Higgs, or even the Higgs itself, could have driven the exponential expansion of the universe just moments after the Big Bang, smoothing everything out. And the way the Higgs field turned on as the universe cooled, that electroweak phase transition would have fundamentally changed the laws of physics, allowing particles to acquire mass. Understanding this transition is key to understanding our cosmic history.
Could it be linked to dark energy, too?
That's more speculative, but yes.
Yeah.
Dark energy seems related to the energy of the vacuum itself. The Higgs field contributes to the vacuum energy. Is there a connection? Is dark energy related to some other incredibly light scalar field? These are huge open questions where particle physics and cosmology overlap.
It all connects. Smallest scales, largest scales.
That's the beauty of fundamental physics.
What an incredible story from a theoretical puzzle about mass in the 1960s.
Through decades of painstaking searches, near misses.
To the monumental engineering of the LHC and its detectors.
And finally, that triumphant discovery in 2012, a testament to global collaboration, ingenuity, and just sheer persistence.
But as you said, the Higgs isn't the end. It's a beginning.
Absolutely.
Right.
It's a landmark, no doubt. It completes the standard model particle inventory. But more importantly, it opens up this entirely new realm, the scalar world. It gives us a powerful new tool, a new lens to probe the universe's deepest mysteries.
Dark matter, dark energy, unification of forces. The Higgs is now central to tackling those questions.
It is. Its properties, its mass, its stability. They are all clues we need to decipher.
And here's the really provocative thought to leave everyone with. The fact that we found only the standard model Higgs, nothing else alongside it.
That might be the most shocking and, in a way, the most exciting outcome.
More exciting than finding supersymmetry.
Arguably, yes. Because it challenges our assumptions more deeply. It tells us nature might be playing by different rules than we thought. It forces a more fundamental rethink. It means the path forward is less clear, more challenging, but potentially even more rewarding in terms of fundamental understanding.
We're in uncharted territory, in a sense.
We really are. It's a unique time in science. The questions are profound, almost existential. What is the nature of reality? Why is the universe the way it is? The path forward requires new ideas, perhaps new experimental approaches. It's tough, but incredibly exciting.
As one physicist put it, a fantastic time to be a physicist if you're in it for the long haul.
Couldn't agree more. The challenges are immense, but the potential for discovery, for truly changing our view of the universe, is just staggering.
Well, we hope this deep dive has given you a solid grasp of this incredible scientific journey and maybe sparked your curiosity to explore even further.
There's so much more to learn.
Indeed. Until next time on the deep dive, keep asking the big questions. We're talking about the groundbreaking discovery of the Higgs boson at CERN. We've really gone deep into an extensive stack of sources for this. I mean, everything from the original seminal research papers published by CERN's own Atlas collaboration.
Yeah, primary sources.
To the really personal perspectives from leading physicists who lived this whole quest, people like Xiaolan Wu, which offer such a unique insight, and also the illuminating viewpoints from places like the World Science Festival and the Royal Institution.
So yeah, we're going to unpack it all. We'll look at the theoretical ideas that kind of made this particle seem almost necessary.
Yeah.
Then the decades-long, sometimes really frustrating experimental search, trying to actually find it. We'll talk about the truly groundbreaking technologies. These weren't just tools, they were engineering marvels in their own right. And crucially, the profound implications, not just of finding the Higgs, but maybe even more importantly, of finding only the Higgs. That's a big part of the story later on.
Okay, let's dive in then, because really, to grasp why the Higgs boson discovery was such a huge deal, we first need to understand the sort of fundamental recipe book for our universe. That's the standard model of particle physics.
Right. Think of the standard model as, well, it's our current best understanding, our most comprehensive picture of what everything is fundamentally made of. And just as importantly, what forces hold all that stuff together. It's an incredibly successful theory, really. Is what physicists call a quantum field theory, and it's built on this really powerful mathematical framework based on symmetry groups. It sounds complex, but it's essentially a very precise language for describing interactions.
And what's really neat, I think, is how elegantly it classifies all the known fundamental particles. It basically sorts them into two main families, the fermions and the bosons.
Exactly. Let's start with the fermions. These are the guys we call the matter particles. I mean, literally, they are the building blocks of everything tangible. You, me, this microphone, the planet, all of it. And they all share a quantum property called spin 12.
Okay, and spin here, it's important to clarify this, right? It's not like a tiny ball actually spinning around. These particles are thought to be point-like, essentially zero size. So spin is more like an intrinsic angular momentum, a fundamental property like charge or mass.
Precisely. It's just part of what they are. And within the fermions, you've got two subgroups. First, the quarks. There are 6 types, or flators: up, down, strange, charm, top, and bottom. Then you have the leptons, again, 6 of them. The familiar electron, then the heavier muon and tau particles, plus their 3 corresponding neutrinos, the electron neutrino, muon neutrino, and tau neutrino.
And it's kind of mind-blowing when you stop and think about it.
Yeah.
You, me, everything we see and touch in our daily lives, fundamentally it's all just made up of electrons and those tiny up and down quarks. That's it.
Pretty much. All the complex chemistry and biology boils down to those few ingredients interacting. Then the other family, the bosons. These are the force-carrying particles. Unlike fermions with their half-integer spin, bosons have integer spin, typically spin 1. The most famous example, the photon. That's the boson that carries the electromagnetic force.
Right, the force responsible for electricity, magnetism, light, holding atoms together, all of chemistry, basically.
Exactly. Then you've got the gluon. There are actually 8 types of gluons, and they carry the strong nuclear force. This is the incredibly powerful force that binds quarks together inside protons and neutrons and also holds the nucleus of an atom together. Super important.
And the last ones?
The W and Z bosons. There are 2 Ws, W plus and W, and 1 Z. They mediate the weak nuclear force. The weak force is responsible for certain types of radioactive decay and processes like nuclear fusion in the sun. It allows particles to change their identity, like a neutron turning into a proton.
Okay, so we have this incredibly elegant picture. Matter, particles, fermions, and force carriers, bosons. The standard model describes them beautifully, but for decades there is this huge, glaring problem right at its heart, a real enigma, the mystery of mass.
Yes, this was the big headache.
Hmm.
The Standard Model, in its, let's say, purest mathematical form, actually predicted that all these fundamental particles should be massless, which is obviously wrong. We know electrons have mass, quarks have mass.
So how did they try to fix it? Just add mass in by hand?
Well, they tried. But when you simply inserted mass terms into the equations for the fundamental particles, particularly for the W and Z bosons, it broke something really fundamental. It violated a core principle called gauge invariance.
And gauge invariance is crucial, right? It's tied to the fundamental forces themselves.
Absolutely crucial. It's a kind of mathematical symmetry that ensures the theory behaves consistently. If you break gauge invariance, the theory basically falls apart. You start getting nonsensical predictions like probabilities adding up to more than 100%. Technically, the theory becomes non-renormalizable. You just can't do calculations reliably. It was a showstopper.
Wow. So you have this beautiful theory that works perfectly, unless you try to include mass, which we obviously know exists.
Exactly. And beyond just allowing for mass, the theory gave absolutely no clue why particles have the specific masses they do. Like you mentioned, why is the muon, which seems like just a heavier version of the electron, about 200 times heavier? Why is the top quark so incredibly massive, heavier than a gold atom? The Standard Model, pre-Higgs, was completely silent on this. The masses were just numbers you had to plug in from experiments with no underlying explanation.
Okay, so the stage is set, a huge theoretical hole. And this is where the breakthrough idea comes in, right? The Higgs mechanism.
Precisely. This was the revolutionary concept proposed back in 1964. It actually came from several groups of physicists working independently around the same time. Most famously, Robert Brout and Francois Englert in Brussels, and Peter Higgs in Edinburgh. Also, Gerald Guralnick, Carl Hagen, and Tom Kibble in London published similar ideas. It was a moment of parallel insight.
And their radical idea was?
Their radical idea was that the vacuum, what we think of as empty space, isn't truly empty. Instead, they proposed, the entire universe is permeated by an invisible, omnipresent field. We now call it the Higgs field.
Okay, an invisible field everywhere. How does that help with mass?
Well, the most common analogy, and it's actually a pretty good one, is to think of this field like cosmic molasses or treacle, filling all of space. Now imagine particles trying to move through this molasses.
Okay, they'd experience some resistance, some drag.
Exactly. And according to this idea, that resistance, that interaction with the Higgs field, is what we perceive as mass. Particles that interact very strongly with the Higgs field, like the very heavy top quark, feel a lot of drag. They are massive. Particles that interact weakly, like the electron, feel only a little drag. They have a small mass.
And particles like the photon, the carrier of light.
Photons, crucially, do not interact with the Higgs field at all. They feel no resistance. And that's why they remain massless, free to travel at the ultimate speed limit, the speed of light, completely unimpeded by the cosmic molasses.
That's a really elegant explanation. So the Higgs field is the molasses spread everywhere. What about the Higgs boson then? Where does that fit in?
Good question. The Higgs boson is the particle associated with this field. It's the quantum excitation of the field. Think of it like this. The electromagnetic field exists everywhere, right? And a photon is a ripple, a quantum, a little packet of energy in that field. Similarly, the Higgs field is everywhere, and the Higgs boson is a ripple, a quantum, a detectable excitation of that field.
So finding the Higgs boson would be the proof that this Higgs field, this cosmic molasses, actually exists.
Exactly. It's the smoking gun. If you can create and detect a Higgs boson, it confirms the existence of the underlying field that gives mass to everything else. Mathematically, the beauty of this Higgs mechanism is how it allows particles, especially the W and Z bosons, to acquire mass without breaking that crucial gauge invariance we talked about earlier.
How does it manage that?
It involves something called spontaneous symmetry breaking. The underlying equations of the theory still possess the full electroweak symmetry, but the lowest energy state of the universe, the vacuum state itself, doesn't respect that symmetry. The Higgs field has a non-zero value even in its lowest energy state. We call this the vacuum expectation value, or VEV. It's about 246 giga-electron volts, or GeV.
Okay, so the laws are symmetric, but the state of the universe isn't.
Kind of like that, yes. Imagine a perfect circle drawn on a piece of paper that's symmetric. But if you place a pencil upright exactly in the center, it's unstable. It will inevitably fall over in one specific direction, breaking the rotational symmetry, even though the underlying rules allowed for any direction. The Higgs field, having this non-zero VeV, breaks the electroweak symmetry, SU LDR times U1Y, down to just the electromagnetic symmetry that we observe. And it's this spontaneous breaking that cleverly generates mass for the WZ bosons and allows for fermion masses via their interaction with the Higgs field, all while keeping the theory mathematically consistent and renormalizable.
Wow. That's incredibly clever. It solves the mass problem without destroying the theory.
It was a theoretical masterstroke. It really addressed what some called Newton's unfinished business, the fundamental origin of mass. But of course, it was just a theory. An elegant one, sure, but it all hinged on whether this new particle, the Higgs boson, actually existed. And finding it, well, that was going to be tough.
Which leads us perfectly into the long, arduous search. Decades of hunting for this elusive particle.
Yes, and one of the biggest hurdles, as physicist Xiaolan Wu emphasized in her accounts, was simply not knowing how heavy the Higgs boson was supposed to be. Theory didn't pin down its mass. It could have been relatively light or incredibly heavy. As she pointed out, we know the electron's mass, the muon's mass, but we don't fundamentally understand why they have those values. Same for the Higgs. Its mass was a complete unknown.
So experimentalists were basically searching in the dark, across a huge range of possible energies.
Pretty much. They had to design experiments capable of looking everywhere, from low masses up to potentially very high masses. The first sort of glimmer of hope, though it turned out to be a false dawn, came back in the early 80s, 1984 specifically. It was from the Crystal Ball collaboration, working at the Doris Collider at DSY in Germany.
What did they see?
They were looking at the decays of a heavy particle called the upsilon meson, which is made of a bottom quark and its antiquark. They were searching for a specific decay, upsilon Higgs plus photon. And remarkably, they saw a distinct peak in the energy spectrum of the photons, which seemed to correspond to a Higgs boson with a mass of about 8.32 GeV.
8.32 GeV. That's relatively light, isn't it?
Yes, compared to what we know now, it's quite light. And the incredible thing was the statistical significance of their peak was reported as being over 5 sigma.
5 sigma, that's the gold standard for discovery, even today.
Exactly. So you can imagine the excitement. Was this it? Had they found the Higgs already?
Yeah.
It generated a huge amount of buzz in the particle physics community.
Wasn't it?
Unfortunately, no. Subsequent experiments, like the CUSB collaboration at Cornell, tried to confirm the signal using their own detectors and data, but they couldn't find it. And as the crystal ball experiment itself collected more data, their own peak started to, well, fade away. It turned out to be just a statistical fluctuation, a cruel trick of the numbers.
That must have been disappointing.
Hugely disappointing. But it's part of the process. You need independent confirmation. Other searches in the 1980s by experiments like Syndrome and Clio also looked for a light Higgs in different decay modes, like decaying to muon pairs or pion pairs. They all came up empty-handed. So by the end of the 80s, the consensus was growing that if the Higgs existed, it had to be heavier than about 8 or 9 GeV card. The hunt had to move to higher energies.
And that's where CERN comes back into the picture in a big way, with the Large Electron-Positron Collider, LEP.
Exactly. LEP was the next great hope. Xiaolan Wu, in fact, specifically moved to CERN to join the ELAIF experiment at LEP precisely because she wanted to be at the forefront of the Higgs search. She jokes that she didn't realize then it would turn into a personal 32-year quest for her.
32 years, wow. And LEP itself was a monster machine for its time, right? That 27-kilometer ring under Switzerland and France.
Oh, absolutely. A true engineering marvel. It collided electrons and positrons head-on. Its first phase, LEP-1, ran from 1989 to 1995. It was tuned to operate right at the energy needed to produce Z bosons, about 91.1 H-GeV. This was fantastic because LEP became a Z factory, producing millions upon millions of Z bosons.
And how did that help the Higgs search?
Well, one way the Higgs could be produced at LEP-1 was through a rare Z boson decay, Z Higgs plus a pair of leptons, electrons and muons. That's ZA plus I. These events would be very clean, very distinctive experimentally. Another channel was Z Higgs plus a pair of neutrinos. CO Hyde. This happened more often, had a larger branching ratio, but was harder to detect because neutrinos just fly off unseen.
So did LEP-1 find anything?
No, unfortunately. By analyzing all the Z decays, the 4 LEP experiments, Aleph, Delphi, L3, and Opal, were able to collectively rule out a Higgs boson with a mass below about 65 GeV. They pushed the lower limit up significantly.
Okay, so phase 2, LEP-2.
Right. From 1995 to 2000, CERN upgraded LEP to operate at much higher energies, eventually reaching up to about 209 GeV center of mass energy. This was crucial because it opened up a new production mechanism: electron plus positron Higgs plus Z boson, E plus E HEZ. Now you could produce the Higgs alongside a real Z boson.
A different way to make it. And did they have specific decay channels they focused on?
Yes, the most sensitive channel at LEP2 turned out to be when the Higgs decayed into two bottom quarks, age, and the Z boson also decayed into quarks, Z-few, leading to a final state with 4 jets of particles. They also looked for channels where the Z decayed into leptons or neutrinos. And as LEP2 collected more and more data at higher energies, they kept pushing that lower mass limit higher and higher. By 1999, they had excluded a Higgs mass below 107.9 GeV air with 95% confidence.
They were really closing in on a specific range.
They were. And the tension, the excitement became almost unbearable in the year 2000. The ALEH experiment reported seeing a small cluster of events that looked tantalizingly like a Higgs signal, right around a mass of 114 GeV phase.
Wow, another potential signal. After the crystal ball experience, were they cautious?
Extremely cautious, but also hopeful. The other experiments saw some slight excesses in the same region, though not as strong as ALEH's. It was enough for the combined LEP-Higgs working group to make a formal, rather desperate request to CERN management. Could they please extend LEP's run by just 4 to 6 months into 2001? They argued that just a little more data might be enough to confirm or refute this 114 GeV hint.
That sounds reasonable. What happened?
The request was denied. The shutdown schedule for LEP was already firmly in place, primarily because they needed to dismantle it to start building its successor in the same tunnel, the Large Hadron Collider, the LHC. So in November 2000, LEP was switched off for the last time, leaving that 114 GeV hint hanging unresolved, a real cliffhanger.
Oh, man. So close, potentially. The search then moved across the Atlantic.
Yes. For the next decade, roughly 2001 to 2011, the only machine in the world capable of potentially producing and discovering the Higgs was the Tevatron Collider at Fermilab near Chicago. The Tevatron collided protons and antiprotons at very high energies for its time, reaching nearly 2 TeV center of mass energy.
And it had 2 big detectors, CDF and D0.
That's right, 2 large, sophisticated experiments hunting for the Higgs. The Tevatron had already had major successes, like discovering the top quark in 1995. Hopes are high it could find the Higgs too.
But it didn't quite get there, did it?
It didn't. It came very close. The primary reason, looking back, was that it just couldn't collect enough data fast enough. It needed more integrated luminosity, more collisions recorded. Estimates suggest it probably needed about 2.5 times the total data it actually managed to accumulate over its lifetime.
So it wasn't the energy, it was the sheer number of collisions.
Mostly, yes. Energy was sufficient for the mass range, where the Higgs eventually turned up. But the Higgs production rate in proton-antiproton collisions is small, and the backgrounds are huge. You need a massive data set. Interestingly, both CDF and D0 did see a persistent, broad excess of events in the mass range between about 120 and 135 GeV, consistent with where the Higgs was eventually found. But the excess never reached that crucial 5 sigma level of significance needed to claim a discovery. It remained a tantalizing hint, much like the LEP signal, until the Tevatron was finally shut down in 2011.
Okay, so LEP hints, Tevatron hints. The pressure and anticipation must have been immense by the time the LHC was ready to turn on.
Absolutely enormous. The entire particle physics community was pinning its hopes on the LHC. And CERN itself, the European Organization for Nuclear Research, is just an incredible place. It's not just a lab. It's a truly global village dedicated to science.
Yeah, you mentioned the scale earlier. 2,500 staff, 7,000 visiting scientists from over 40 countries. It's like a small city focused on physics.
It really is. And the LHC itself, well, it's hard to overstate the scale. The world's largest, most complex machine ever built. That 27-kilometer ring, 100 meters underground, straddling the border between Switzerland and France.
It's been called the world's fastest racetrack, a supermicroscope, even cosmic DNA.
All fitting descriptions. It accelerates protons to incredible energies, allowing us to probe distances smaller than anything before. And by colliding them at such high energies, it recreates conditions similar to those just fractions of a second after the Big Bang, like 10 or 80 seconds after. So we're literally looking back at the universe's infancy.
The engineering behind it is just staggering. Those superconducting magnets, 1,232 of them.
Yep, the main dipole magnets that steer the beams, each one 15 meters long, and they operate at 8.3 cent. Tesla, that magnetic field is 200,000 times stronger than Earth's. To achieve that, they need to be superconducting, which means cooling them down to just 1.9 Kelvin. That's minus 271 degrees Celsius. colder than outer space.
Using superfluid helium, that sounds exotic.
It is. Helium cooled below about 2.2 for Hector. Kelvin enters this weird quantum state, superfluidity, which is incredibly efficient at conducting heat away. It's essential for keeping those magnets stable. And you mentioned this earlier, it's amazing when they cool the whole 27-kilometer ring down, the metal contracts so much that the circumference shrinks by 30 meters.
30 meters, how do they keep everything aligned?
With incredible precision engineering and constant monitoring and adjustments, the alignment tolerance is measured in microns, millionths of a meter. It's unbelievable. And the energy stored? It's immense. 10.4 gigajoules just in the magnetic fields. That's like an A380 jumbo jet cruising at 700 kilometers.
And the beams themselves, all those protons whizzing around.
The two beams circulating contain about 362 megajoules when at full energy and intensity. That's achieved with thousands of bunches of protons, 2,808 bunches per beam in the design. Each bunch contains something like 100 billion protons, all accelerated up to 7 TeV per beam, giving 14 TeV collision energy eventually.
And where do all these protons even come from?
It starts surprisingly simply. A standard bottle of hydrogen gas. That's enough fuel to run the LHC for weeks. They strip the electrons off the hydrogen atoms to get protons. Then these protons go through a whole chain of smaller, older accelerators at CERN. First the LINAC, then the proton synchrotron booster, PSB, then the proton synchrotron CPS, then the super proton synchrotron SPS. Each one kicks the energy higher and higher before finally injecting the beams into the main LHC ring.
It's like a multi-stage rocket, but for protons.
Exactly. And by the time they're colliding in the LHC, they're traveling at 99.999991% of the speed of light, just fractionally slower than light itself.
Incredible, but it wasn't all smooth sailing from the start, was it? There was that major incident in 2008.
Ah, yes. September 19th, 2008. A date etched in the memory of everyone involved. The LHC had only just circulated its first beams a few days earlier, a huge celebration. Then disaster struck during powering tests. A faulty electrical connection, basically a bad solder joint between two of the superconducting magnets, melted under the high current.
Melted at 1.9 Kelvin.
Well, it heated up rapidly, causing it to lose superconductivity. This created electrical resistance, which generated more heat, leading to an electrical arc. The arc punctured the helium enclosure, causing a massive explosive release of tons of super-cold helium gas into the tunnel. It caused significant mechanical damage to dozens of magnets, shifted huge components. It was a major, major setback.
That sounds terrifying and devastating for the project.
It was both. There were fears it could delay the project by years. But the response was phenomenal. It took about 15 months of incredibly hard work, removing damaged magnets, repairing them, installing new safety systems, rigorous retesting to get things back online.
But during that long repair period, the big experiments, ATLS and CMS, they weren't just sitting idle, were they?
No, that's a crucial point. While the accelerator was being fixed, the detector teams used that time extremely productively. They kept their detectors running, recording data from cosmic ray muons. These are high-energy particles from space that constantly shower down on Earth, even penetrating 100 meters underground.
So they used cosmic rays for calibration.
Exactly. Hundreds of muons pass through the detectors every second. They use these tracks to precisely align all the different detector components, calibrate the electronics, understand the detector performance inside out. So when the LHC beams finally came back in November 2009, the detectors were arguably even better prepared than they would have been without the delay. They turned a potential disaster into a crucial commissioning phase.
That's resilience. And when the collisions finally started, Run 1.
Yes, Run 1 lasted technically from late 2009 to early 2013. They started with lower energy collisions, then ran mostly at 7 TeV center of mass energy in 2010 and 2011. Then, crucially for the Higgs discovery, they pushed the energy up to 8 TeV for the 2012 run. And the performance of the LHC during this period was actually better than expected. They collected about 25 inverse femtobarns of data in total for ATLAs and CMS by the end of Run 1.
Inverse femtobarns, that's the measure of collected data, right? More is better for finding rare things.
Precisely. Think of it as the number of lottery tickets you've bought. The more you buy, the better your chance of winning, especially for a rare jackpot like the Higgs. Then, after a long shutdown for upgrades, Run 2 started in 2015 and ran until 2018. Here, they pushed the energy up to 13 TeV and significantly increased the intensity, the luminosity. They actually reached peak luminosities twice the original design specification. Over Run 2, they accumulated a massive data set, around 140 inverse femtobarns.
And the sheer rate of collisions is mind-boggling, isn't it? Billions per second.
Yeah, at peak performance, around a billion proton interactions every single second inside the detectors. It's an incredible fire hose of data. Now remember, the Higgs particle is only expected to be produced in maybe 1 out of every 10 billion of those collisions.
Talk about a needle in a haystack. Which brings us to the eyes of the LHC, the detectors designed to find that needle. ATLS and CMS.
Right. These are the two behemoths, the general-purpose detectors, located at two of the main collision points around the LHC ring. General purpose meaning they're designed to look for anything and everything. The Higgs, supersymmetry, extra dimensions, unexpected surprises, and they are enormous. Roughly the size of a 5-story building, weighing thousands upon thousands of tons.
And their job is basically to take incredibly fast, detailed 3D photographs of the debris flying out from each collision.
That's a good way to put it. They need to detect as many particles produced as possible, measure their trajectories, their energy, their momentum, identify what type of particle they are, electron, muon, photon, jet of hadrons. Then sophisticated software reconstructs the whole event, trying to piece together what happened right at the collision point.
And a key point is that ATLS and CMS are completely independent, designed, and built differently.
Absolutely vital. They were built by separate international collaborations, numbering thousands of scientists and engineers each. They deliberately chose different technological solutions for their magnets, their tracking systems, their calorimeters, which measure energy. This means if both experiments, using different techniques, see the same new phenomenon like a bump at a certain mass, you can be much more confident it's real physics and not just some glitch or artifact in one detector. It provides crucial cross-checking.
Okay, let's look at ATLS briefly. What's its design philosophy?
ATLAS uses a very distinctive magnet system. It has huge air-core toroid magnets arranged like barrels around the outside to bend the paths of muons. These provide a 0.5 Tesla field. Then, closer to the collision point, it has a smaller solenoid magnet providing a 2 Tesla field, mainly for tracking charged particles accurately. Inside these magnets, it's layered like an onion. Innermost is the tracking detector, silicon pixels, silicon strips, and straw tubes to get precise particle tracks. Outside that are the calorimeters, a liquid argon electromagnetic calorimeter to measure electrons and photons, and then hadronic calorimeters. And finally, the large muon spectrometer, using those toroid magnets. It weighs about 7,000 tons, is 25 meters high and 44 meters long. A giant. Okay, air core toroids and a solenoid for ATLS. What about CMS compact muon solenoid? Yes, CMS stands for compact muon solenoid, and its name hints at its design. Its heart is one single, incredibly powerful superconducting solenoid magnet. This solenoid is huge and generates a very strong, very uniform 4 Tesla magnetic field throughout its central volume, much stronger than the ATLS solenoid.
4 Tesla, that's enormous.
It is. This strong field bends charged particle tracks very tightly, allowing for excellent momentum measurement within a more compact detector volume, hence the compact in CMS. Inside the solenoid, CMS also has layers, a high-precision, all-silicon inner tracker, then a stunning electromagnetic calorimeter made of lead tungstate crystals. These give superb energy resolution for electrons and photons. Outside that, a brass and scintillator hadron calorimeter. And the magnet's massive iron return yoke itself is instrumented with muon detectors, gas chambers, interleaved within the iron. CMS is actually much heavier than ATLAS, despite being more compact, about 12,500 tons. It contains enough iron, famously, to build 2 Eiffel Towers.
2 Eiffel Towers. And didn't they build CMS in a unique way, assembling it on the surface?
Yes, that was a pioneering feat of engineering. Most of CMS was assembled and tested above ground in huge, complete sections. These massive slices, weighing up to 2,000 tons each, were then carefully lowered down the 100-meter shaft into the underground cavern using a specialized heavy-lifting gantry system. It was a way to manage the complexity and ensure quality control before installing it underground. Quite remarkable.
So these incredible machines were built, installed, and then commissioned using those cosmic rays we mentioned earlier and known physics processes.
Exactly. First, cosmic rays to check connections, timing, alignment. Hundreds per second raining down gave them plenty of tracks to work with. Then, once the first LHC collisions started, even at low energies, they focused on rediscovering well-known particles and processes predicted by the standard model, things like W bosons, Z bosons, top quarks. These act as standard candles. Because we know precisely how often they should be produced and how they should decay, observing them correctly confirms that the detectors are understood and working as expected. Once they could reliably measure these known processes, they could declare the detectors physics commissioned, ready to hunt for the unknown, like the Higgs.
Okay, the stage is set, the machines are ready. Let's talk about the Higgs itself. Its life is incredibly short, right?
Unimaginably short. The standard model predicts its lifetime to be around 1.6 by 10 seconds. That's less than a trillionth of a second. It decays practically the instant it's created. It travels maybe the width of a proton before vanishing.
So you never, ever see the Higgs boson directly in the detector.
Never. It's long gone. What we see are its decay products, the more stable particles it transforms into. So the whole game is about reconstructing the properties of the Higgs like its mass, by meticulously measuring the energy and momentum of those decay products and working backward.
And this is where the needle in a haystack problem really bites, because Higgs production is so rare and its decay products are often common particles.
Precisely. Out of those billion collisions per second, maybe only a handful produce a Higgs. And the things it decays into, like pairs of photons or Z bosons or W bosons or bottom quarks, are also produced in vast quantities by much more common, boring background processes. So you're looking for a tiny, tiny signal bump sitting on top of a mountain of background noise. It requires incredibly sophisticated analysis and understanding of all those background processes.
Okay, let's break down how the Higgs is actually made at the LHC. What are the main production mechanisms?
The number one dominant process by far is something called gluon fusion, often abbreviated GGF. This accounts for something like 87% of all Higgs bosons produced at the LHC.
Gluon fusion. So two gluons from the incoming protons smashed together.
Essentially, yes. But it's a bit more subtle. It happens via a quantum loop. The gluons don't directly couple to the Higgs. Instead, the interaction is mediated primarily by a loop of virtual top quarks. A gluon splits into a top-anti-top pair. The Higgs interacts with the top quarks because the top is so heavy, this interaction is strong. And then the top-anti-top pair annihilates back into the other gluon. So, paradoxically, the heaviest quark, the top quark, plays the most crucial role in producing the Higgs, even though it's much heavier than the Higgs itself.
That's fascinating. What's the next most common way?
That would be vector boson fusion, or VBF. This accounts for about 7% of Higgs production. Here, two quarks inside the protons each radiate a W or a Z boson. These two vector bosons then fuse together to create the Higgs boson.
Vector boson fusion, does that leave any special signature in the detector?
It often does. The two quarks that emitted the WZ bosons tend to continue traveling mostly forward, down the beam pipe. This results in two characteristic jets of particles appearing at large angles in the forward and backward regions of the detector, with the Higgs decay products typically found in the central region between them. This distinctive topology helps distinguish VBF events from the dominant GGF background.
Okay, GGF 87%, VBF 7%. What else?
There's associated production where the Higgs is produced alongside a W or a Z boson, often called VH production, V for vector boson. This makes up about 5% of the total. So you see the Higgs decay products plus the decay products of a W or a Z. This can be very useful, especially when the W or Z decays to leptons, which gives a clean tag.
And the rarest one?
The rarest, but conceptually very important one, is associated production with a pair of top quarks, so TTH production. This accounts for only about 1% of Higgs production. It's really hard to find, but it's absolutely crucial because it directly probes the coupling of the Higgs boson to the top quark, its interaction strength. Remember, the top is the heaviest particle, so this coupling is predicted to be the strongest. Testing this coupling precisely is a key test of the standard model, and any deviation could strongly hint at new physics.
And have they actually managed to observe this rare TTH process?
Yes. It was a major achievement, announced a few years after the initial discovery. Both ATLACE and CMS have now observed TTH production with high statistical significance over 5 sigma each. Confirming that the Higgs does indeed couple to the top quark as expected, or very close to it, was a huge milestone.
Amazing. So the Higgs is produced in these various ways, then instantly decays. What are the key decay channels that the experiments looked for, especially for the discovery?
For the discovery itself, the experiments relied heavily on channels that offered very high mass resolution and relatively low background noise, even if they weren't the most frequent decays. The cleanest channels.
The so-called golden channel was the 4-lepton one, right? H is a rho?
Exactly. H to ZZ star to 4 leptons, electrons or muons. The star indicates that one of the Z bosons can be off-shell or virtual, meaning it doesn't have the full Z boson mass because the Higgs mass, 125 GeV, isn't quite enough to make two real Z bosons, each about 91 GeV. But this decay mode is beautiful experimentally. 4 high-energy leptons, electrons, or muons originated from a single point. It's an incredibly clean signature.
Even though it's quite rare, only about 2.6% branching ratio.
Yes, the branching ratio is tiny. Out of roughly 400 Higgs bosons produced, only one will decay this way. But the background noise for seeing 4 isolated high-energy leptons is also very, very low in the standard model. So when you do see such an event, you can reconstruct the invariant mass of the 4 leptons with fantastic precision, and if it consistently peaks at a certain value, that's a very strong signal. The analysis requires demanding that the leptons are well isolated, have high transverse momentum PT, and that pairs of them reconstruct near the Z mass.
Okay, the golden channel was the other key discovery channel, the 2-photon one.
Yes, H to gamma gamma.
Yeah.
Higgs decaying into 2 high-energy photons. This one is even rare. The branching ratio is only about 0.2%, so like 1 in 500 Higgs decays.
Why is it so rare? Doesn't the Higgs couple directly to photons?
No, that's the interesting part. The Higgs has no electric charge, so it doesn't directly interact with photons. This decay happens via quantum loops, just like the gluon fusion production. In this case, the loops involve virtual W bosons and top quarks. The Higgs fluctuates into these heavy particles, and they then radiate the photons.
Ah, so it's an indirect decay. Does that make it sensitive to new physics, too?
Very much so. If there were other undiscovered, heavy charged particles that the Higgs couples to, they could also contribute to that loop, potentially changing the A-gay decay rate compared to the standard model prediction. It's a great place to look for subtle signs of new physics. Experimentally, despite its rarity, it's also a very clean channel. 2 high-energy photons in the electromagnetic calorimeter pointing back to the collision vertex. You can measure their energies very precisely and reconstruct the Higgs mass with excellent resolution, similar to the 4-lepton channel.
So these 2 4-leptons and 2 photons were the workhorses for the initial discovery because of their cleanliness and good mass resolution.
Absolutely. They allow the experiments to see clear, narrow peaks rising above the background right around 125 GeV.
What about other decays? You mentioned HWW. That has a large branching ratio, right? Around 21%.
It does. It's the second most frequent decay after He, Higgs to W plus W minus, but it's much trickier experimentally. Why? Because W bosons often decay into a lepton, electron or muon, plus a neutrino. And neutrinos are notoriously difficult to detect. They just fly straight through the detector without interacting, carrying away energy and momentum.
So you can't fully reconstruct the event. You have missing energy.
Exactly. You see the leptons, but you don't know exactly how much energy and momentum the neutrinos took. This smears out the reconstructed mass of the Higgs. You don't get a sharp peak like you do in the 4-lepton or diphoton channels. It's more of a broad excess. If the W's decay hadronically into quarks jets, the background for normal QCD jet production is enormous, so the leptonic decays are preferred, despite the neutrinos.
Okay, what about He++ decay to tau leptons? About 6% branching ratio.
Similar story there. Tau leptons are also unstable and decay quickly, often involving neutrinos in their decay products, whether they decay leptonically or hadronically. So again, you have missing energy, which degrades the mass resolution. It's an important channel to study Higgs couplings to leptons, but harder for discovery.
And the most common decay of all, H-heads Higgs to a bottom quark and an antibottom quark. Over 50% branching ratio.
Yes, around 58%. The Higgs loves to decay into bottom quarks because they are relatively heavy compared to the other quarks and leptons, though much lighter than the top. But this channel is absolutely swamped, buried under an avalanche of background. Why? Because regular strong force interactions, QCD, produce pairs of bottom quarks all the time at the LHC, at a rate something like 10 million times higher than the rate from Higgs decays.
10 million times? How can you possibly see the Higgs signal in that?
It's incredibly challenging. You can't just look for any 2 B-quark jets. The trick is to look for HA in association with something else that helps you tag the event and reduce the background. For example, look for VH production, where the Higgs is produced alongside a W or Z boson. If that W or Z decays leptonically to electrons, muons, or neutrinos, that provides a clean tag. You then look for 2 B-quark jets accompanying those leptons. This drastically cuts down the QCD background, allowing the small HA signal to eventually emerge with enough data. It took several years after the initial discovery to confirm the HMBK.
Right. So the discovery relied on the clean, rare channels, and the characterization uses all of them, even the messy ones.
That's a good summary. You need the clean ones to find it, then you need all of them to understand it.
Which brings us to the moment itself, July 4th, 2012, the announcement. But the hints started earlier, didn't they? December 2011.
That's right. In December 2011, both ATLS and CMS presented preliminary results based on their 2011 data, taken at 7TV. And independently, both experiments reported seeing tantalizing hints that was the carefully chosen phrase, of an excess of events around 125 GeV. The excess was seen in both the AG and HEUV channels. It wasn't statistically significant enough to claim discovery yet, maybe around 2-3 sigma individually, but the fact that both experiments saw hints in the same mass region in multiple channels, that got everyone very excited.
The scent of discovery was in the air.
Palpably. It set the stage for the crucial 2012 run. As we mentioned, they increased the LHC energy to ATV in early 2012, which slightly increases the Higgs production rate. And they started collecting data like crazy. The pressure was immense to analyze this new data quickly, but also incredibly carefully.
And they used blind analysis techniques, right, to avoid bias.
Absolutely critical. The analysis teams defined all their event selection criteria, their background estimation methods, their statistical procedures based on simulations before they were allowed to look at the actual new 8TV data in the signal region, around 125 GeV. This prevents any unconscious bias or even conscious temptation to tweak the analysis cuts to enhance a small fluctuation you might see in the data. You have to pre-commit to your method.
So the moment of truth was when they finally unblinded the analysis in June 2012?
Yes. After months of accumulating the ATV data, running it through the predefined analysis chains, checking everything meticulously, the moment came to open the box and look at the result in the crucial mass region. And what they saw in both experiments was stunning. The small hints from 2011 had grown into significant, undeniable signals.
Significant enough for the 5 sigma gold standard?
Yes. Remember, 5 sigma means the probability that the observed excess is just a random background fluctuation is less than 1 in 3.5 million, or 1.7 by 10 a year, considering the look elsewhere effect. It's an incredibly stringent requirement. When you plot the invariant mass of the decay products, like the 2 photons or the 4 leptons, the background forms a smooth falling curve. A real particle shows up as a distinct bump or peak rising above that curve. Seeing that bump reach 5 sigma significance is the moment physicists pop the champagne.
And combining data was key, from different channels and the 2 experiments.
Crucial. Individually, maybe one channel in one experiment was close to 5 sigma, but others were less significant. But when ATLs combined the results from HIGO and HWORI, they reached 5 sigma. When CMS combined their results from HIGO and HWORI and also included HWW in their combined result, they reached 5 sigma. The fact that 2 independent experiments, using different detectors and slightly different analysis techniques, both confirmed the signal at the same mass, around 125 GeV, with discovery-level significance. That made the result completely unambiguous.
And led to that historic seminar at CERN on July 4th, 2012. Peter Higgs and Francois Englert in the audience. Must have been electric.
Oh, absolutely. Packed auditorium, thousands watching online worldwide. A truly seminal moment in science. Both the ATLS and CMS spokespersons presented their results back-to-back, each announcing the independent observation of a new boson with a mass around 125 G, consistent with the standard model Higgs. Standing ovations, tears. It was incredibly emotional.
A culmination of 50 years of theoretical work and experimental searching.
And, as you mentioned, the ATLA's collaboration poignantly dedicated their discovery paper to colleagues who hadn't lived to see that day, a reminder of the human endeavor behind it all.
So they found a new particle. The next big question, was it the Higgs boson predicted by the standard model?
Exactly. Finding a bump was step 1. Step 2, which is still ongoing in many ways, is characterizing this new particle in excruciating detail. Does it really behave exactly like the standard model Higgs should? First check, its mass. Both experiments quickly measured it quite precisely, settling around 125 GeV at check.
What about its other properties, like spin? The standard model Higgs should be unique, a scalar particle with spin 0.
Yes, this was a critical test. Is this new particle a scalar, spin 0 positive parity, denoted 0 plus? Or could it be something else, like a pseudoscalar, spin 0 negative parity 0 bar, or even a spin 1 or spin 2 particle? All known fundamental matter particles are spin 12 fermions. All known fundamental force carriers are spin 1 bosons, except the hypothetical graviton, which would be spin 2. A fundamental spin 0 scalar would be truly unique in the particle zoo.
How did they test the spin?
By looking at the angular distributions of its decay products. For example, in the HEZ4 decay, the angles between the outgoing leptons carry information about the parent particle's spin and parity. Both ATLAS and CMS performed sophisticated analyses, comparing the observed angular distributions to the predictions for different spin parity hypotheses, 0 plus 0 plus 0, 1 plus 1, 2 plus area, etc. And they overwhelmingly favored the standard model prediction. Spin 0, positive parity, 0 plus. They were able to exclude alternatives like the pseudoscalar hypothesis with very high confidence. CMS at 99.8% CL, ATLE at 98.0% CL, for example, using early data. Subsequent analyses have made this even stronger. So yes, it really looked like the scalar boson the standard model needed.
Okay, mass checks out, spin parity checks out. What about its interactions, its couplings to other particles? Does it interact more strongly with heavier particles, as the Higgs mechanism predicts?
This is the core of the ongoing Higgs physics program at the LHC, precisely measuring its coupling strengths to all the other standard model particles. The standard model makes very specific predictions. The Higgs coupling strengths to any particle should be directly proportional to that particle's mass. So it should couple strongly to the heavy WZ and top particles, less strongly to bottom quarks and tau leptons, even less to muons, and very weakly to electrons and light quarks, and not at all directly to massless gluons and photons.
How do they measure these couplings? By looking at the rates of different production and decay modes.
Exactly. The rate at which the Higgs is produced via gluon fusion tells you about its coupling to the top quark via that loop. The rate of VBF production tells you about its coupling to W and Z bosons. The rate of VH production also probes WZ couplings. The rate of TTH production directly measures the top quark coupling. Similarly, the branching ratios, the fraction of times it decays into specific final states, measure the couplings involved in those decays. HWW and HEZ measure WZ couplings. HEM measures the bottom quark coupling. HM measures the tau coupling. HE measures the loop involving W and top. A measures the muon coupling.
And what have these measurements shown so far? Is everything consistent with this standard model?
Remarkably, yes. So far, within the current experimental uncertainties, all the measured Higgs couplings are consistent with the standard model predictions. They've confirmed its coupling to W and Z bosons, to top quarks, via production of loops, to bottom quarks, to tau leptons, and even more recently, to the much lighter muon. The observation of HEMO is particularly important, as the muon is much lighter than the other particles the Higgs was seen decaying to, confirming the coupling scales down with mass as expected.
What about decays that haven't been seen yet, like AV to electrons or AB to charm quarks?
The EB is predicted to be incredibly rare because the electron is so light. The branching ratio is tiny, something like 5 parts per million. It's likely beyond the reach of even the high luminosity LHC. EB is also very challenging. The charm quark is heavier than the bottom, so the branching ratio is smaller, around 3%, but the real problem is distinguishing charm jets from the overwhelming background of light quark and gluon jets. It's an active area of research, but very difficult.
So the picture emerging is that this 125 GeV particle looks, walks, and quacks exactly like the standard model Higgs boson.
Pretty much. To the precision we can currently measure, it fits the standard model description perfectly, which is in itself both a triumph and a puzzle.
A triumph because the theory predicted it so accurately. A puzzle because...
Because the standard model, despite its incredible success, is known to be incomplete. It works beautifully for the particles and forces we can see and measure directly, but it tells us absolutely nothing about the vast majority of the universe.
Right, you mentioned this earlier. The standard model only describes about 5% of the universe's total mass energy content.
Exactly. We know from cosmological observations, galaxy rotation curves, gravitational lensing, the cosmic microwave background, that about 27% of the universe is made of invisible dark matter. It interacts gravitationally, holding galaxies together, but it doesn't seem to interact via electromagnetism, so it's dark, or the strong or weak nuclear forces, as far as we can tell. The standard model contains no particle candidate that fits this description.
And the rest, the biggest chunk.
About 68% is even more mysterious. Dark energy. This seems to be some kind of energy inherent in space itself, causing the expansion of the universe to accelerate. Its nature is a complete mystery. Is it Einstein's cosmological constant? Is it some new dynamical field, sometimes called quintessence? We simply don't know. The standard model offers no explanation.
So dark matter and dark energy are huge gaps. What else does the standard model fail to explain?
Several other profound puzzles. For instance, the matter-antimatter asymmetry. The Big Bang should have created equal amounts of matter and antimatter. They should have annihilated each other, leaving just radiation. Yet here we are in a universe made almost entirely of matter. Where did all the antimatter go? The standard model includes some subtle differences between matter and antimatter, CP violation, but not nearly enough to explain the observed imbalance. And then there's the hierarchy problem. Why is gravity so incredibly weak compared to the other forces? like 1030 or 1040 times weaker. It seems unnaturally feeble. The standard model doesn't address this disparity at all, and it doesn't incorporate gravity, of course.
Okay, so finding the Higgs confirms the standard model's mechanism for mass, but it doesn't solve these deeper mysteries.
Not directly, no. And this is where theories beyond the standard model come in. For decades, theorists have been developing frameworks that try to address these shortcomings.
Like supersymmetry or CCY.
The CECY was, for a long time, the leading contender. It proposes a fundamental symmetry between the two types of particles we discussed: fermions, matter, and bosons, forces. For every known standard model particle, CCY predicts a superpartner particle with a spin differing by 12. So quarks have squarks, spin 0, electrons have electrons, spin 0, photons have photinos, spin 12, the Higgs has Higgsino, spin 12, and so on.
A whole shadow world of particles. What would be the benefit of that?
Several potential benefits. First, if these particles exist and have masses around the TeV scale, or the LHC probes, they could help solve the hierarchy problem by canceling out problematic quantum corrections to the Higgs mass. Second, the lightest supersymmetric particle, LSP, if stable and neutral, could be an excellent candidate for dark matter. It fits the profile quite well in many USY models. Third, CELY predicts that the strengths of the three standard model forces, electromagnetic, weak, strong, might actually become equal at very high energies, a grand unification.
So CELY looked really promising. Did the LHC find any evidence for it? Squarks, electrons?
No. That's been one of the biggest surprises and perhaps disappointments from the LHC so far. ATLAS and CMS have searched extensively for signs of supersymmetry in many different channels, and they found nothing. They've set increasingly stringent lower limits on the masses of these hypothetical particles, pushing them to higher and higher energies, often well beyond what the simplest, most natural versions of CELY predicted.
What about other ideas like extra dimensions?
That's another popular avenue. Theories proposing extra spatial dimensions beyond the three we perceive could also potentially explain why gravity is so weak. Maybe gravity spreads out into these extra dimensions, while the other forces are confined to our 3D brain. Some versions of these theories predicted potentially observable consequences at the LHC, like the production of microscopic black holes, or new particles called Kaluza-Klein excitations.
Any sign of those?
Again, no.
No.
Searches for micro-black holes, extra dimensions, and other exotic phenomena predicted by these models have also come up empty so far.
So, this is the shock you mentioned earlier, finding the Higgs, but absolutely nothing else new?
Exactly. For decades, the prevailing wisdom among theorists was that the Higgs boson would likely not be found in isolation. Because of the hierarchy problem and other theoretical arguments, it felt like finding the Higgs must coincide with finding other new physics at roughly the same energy scale, whether it be CECY, extra dimensions, or something else entirely. Something seemed needed to protect the Higgs mass. The fact that the LHC found only a particle that looks exactly like the standard model Higgs, with no accompanying new particles or phenomena up to the energies probed so far, that was profoundly unexpected for many.
It's like we expected a whole new ecosystem, but just found one predicted species perfectly fitting the old description.
Precisely. And it throws down a huge challenge to theorists. Why does the standard model work so well, even up to the energies probed by the LHC? Why is the Higgs mass what it is, apparently stable without obvious help from new physics nearby? It's been called the biggest challenge since the Michelson-Morley experiment failed to find the luminiferous ether, forcing Einstein to develop special relativity. It suggests our underlying assumptions might be wrong in some fundamental way we haven't grasped yet.
So, the discovery, while confirming the standard model, has simultaneously deepened the mystery of what lies beyond it.
In a way, yes. It closed one chapter beautifully but left the next chapter almost completely blank. We know there must be physics beyond the standard model to explain dark matter, dark energy, etc., but the LHC hasn't yet given us clear clues about what it is or where to find it.
Which brings us to the future. What's next for the LHC in particle physics?
The immediate future is the high luminosity LHC, or HL-LHC. This is a major upgrade to the LHC accelerator and detectors planned to start running around 2029. The goal is to increase the luminosity, the collision rate, by another factor of 5 to 7 compared to the original design.
So even more data. How much more?
The aim is to collect a massive data set, around 3,000 to 4,000 inverse femtobarns per experiment by the mid to late 2030s. That's more than 10 times the total data collected so far.
What will all that extra data allow physicists to do?
Two main things. First, precision Higgs measurements. With so many more Higgs bosons produced, they can measure its properties, its couplings, its rare decays with unprecedented precision. They'll search for tiny deviations from standard model predictions that might hint at new physics indirectly. A key goal is to measure the Higgs self-coupling, how Higgs bosons interact with each other, which probes the shape of the Higgs potential itself. Second, the huge dataset will extend the search for new, heavy particles to even higher masses, pushing the direct discovery frontier further.
So the HLLHC is about precision and extending the reach. What about even further in the future? Are there plans for bigger machines?
Yes, there are several ambitious proposals on the table globally. One of the most prominent, particularly in Europe, is the Future Circular Collider, or SCC. This envisions building a new, enormous 100-kilometer circumference tunnel at CERN.
100 kilometers, nearly 4 times bigger than the LHC.
Exactly. In its ultimate stage, the FCC could house a proton collider capable of reaching collision energies around 100 TeV, that's 7 times the energy of the LHC. A 100 TeV machine would be a true discovery machine, capable of directly producing much heavier particles if they exist, potentially revolutionizing our understanding.
Could it also be used as a Higgs factory, like LEP was a Z factory?
Yes, that's actually a key part of the FCC proposal, likely as a first stage, FCCE. By colliding electrons and positrons in the 100-kilometer ring, initially tuned to energies around the Z-pole and the WW threshold, and it's specifically around 240 GeV, optimal for ZH production, it could produce millions, even billions of Higgs bosons in a very clean environment. This would allow for incredibly precise measurements of the Higgs properties, far beyond what even the HL-LHC can achieve, really scrutinizing the standard model to its limits and testing the Higgs' fundamental nature.
It sounds like the quest initiated by the Higgs discovery is far from over.
Not even close. The Higgs boson wasn't the end of the road. It was more like opening a door onto a whole new landscape, the scalar world, as some physicists call it. It's given us a new tool, a new window, to probe fundamental physics.
And you mentioned connections to cosmology, too, the Higgs field in the early universe.
Yes, that's another fascinating frontier. Did the Higgs field play a role in cosmic inflation, that period of hyperexpansion right after the Big Bang? Its potential energy curve has features that could be relevant. Did the universe undergo an electroweak phase transition as it cooled, when the Higgs field turned on and particles acquired mass? The details of that transition could be linked to the matter-antimatter asymmetry problem. And could the Higgs field, or related scalar fields, have anything to do with the mysterious dark energy driving today's accelerated expansion? These are deep questions linking particle physics and cosmology.
So wrapping this up, it's been an incredible story. From a theoretical puzzle about mass in the 1960s, through decades of searching, culminating in the LHC's discovery in 2012.
A truly stunning achievement of global science, technology, and human persistence. Thousands of people collaborating across borders for decades on a single fundamental question.
And the discovery itself, while confirming the standard model, has arguably left us with even deeper questions about the 95% of the universe we still don't understand.
Precisely. The Higgs is a landmark, a new starting point. It opens up avenues to explore dark matter, dark energy, the unification of forces.
Yeah.
The biggest mysteries out there.
And that final provocative thought for our listeners, maybe the most surprising, most challenging, and ultimately most exciting outcome was finding only the standard model Higgs.
I think so. It forces us to confront the standard model's incredible, almost unreasonable success and stability. It challenges decades of theoretical assumptions about naturalness and what should lie beyond. It means the path forward isn't clearly signposted by theory anymore. We need new ideas, new experimental clues. It's a daunting but also thrilling time for fundamental physics.
As you said, quoting that physicist, a fantastic time to be a physicist if you're in it for the long haul.
Definitely. The questions are profound, the challenge is immense, but the potential for rewriting our understanding of reality is just enormous.
Well, we hope this deep dive has given you a solid grasp of this monumental discovery and maybe sparked your curiosity to explore even further. There's certainly a lot more to learn. Thanks for joining us on the deep dive.